Okay, ladies and gentlemen, lesson number 7 is all about earthquakes. So grab your notebook if you haven't already. We will set up. Um, our challenge question for this lesson is what causes earthquakes and how are they measured? So remember that earthquakes are caused by tectonic plates moving past each other. All three types of plate boundaries cause earthquakes to occur. Um, we have looked at this map before when we looked at the volcanoes. It's the same exact map. Notice now that the yellow dots or the yellow squares are right where the volcanoes were. So earthquakes also occur at plate boundaries. Now there are some random ones out in the middle, right, that are not necessarily on plate boundaries. There are some earthquakes that occur on what are called faults or fissures. So sometimes there are small cracks within a plate that can move as the whole plate moves and cause smaller earthquakes. But your really large earthquakes occur right at these plate boundaries. Okay. So how do we measure earthquakes? That would be the next question. So there is a tool called a seismograph, and that tool is used to measure the intensity or the strength of an earthquake. So go ahead and write down that definition. Um, Essentially, what a seismograph is it's a station and it's attached to the ground in different places. You can put one anywhere. They're at the bottom of the ocean, they're on mountaintops, they're on valleys. We have put them all over the globe. And there's an arm on it, and it's weighted, and there's a spring in here. And so what happens is when the ground shakes, the spring moves, right? And it triggers the paper to roll. So once motion is detected, this starts rolling out and the pen scribbles on the paper. So if you look at it from the other side, here's your pen. And as that paper spins, this pen will wiggle back and forth. Okay? This is the machine. The paper that comes out of the seismograph is called a seismogram. So record this definition as well. A seismogram is the lines recorded on paper created by the seismograph. It kind of looks like a scribble. You're probably thinking that it looks a little bit like a heart rate or if you've watched crime shows, sometimes it looks like a voice recording, but those are very similar. They record vibrations. And that's exactly what the seismograph is doing. It's recording the vibrations of the ground. So the bigger the scribble, right, the stronger the earthquake. But scientists needed to collaborate and work together. So to make this data more valuable, we have put seismographs all over the globe. So everywhere you see a red triangle, there's a seismograph there. So they're in the ocean, they're in the Antarctica, they're up in Greenland where it's frozen. They are everywhere. Um, we use that to measure how strong earthquakes are. If an earthquake happens in, let's say, the United States, we're going to measure it in the ocean. We're going to measure it in South America. We're going to measure it over in Asia. It'll go through. So those waves go through the earth. Remember, we talked about in the beginning how we know what the layers are in the earth is by how those waves move through the earth and how they move through those materials. So an earthquake that happens on any place on the planet, we measure at all these different stations. And it gives scientists a good indication of what's going on underneath us. Okay, so just because we have those scribbles, we had to make use of that information. So scientists came up with two scales used to measure earthquakes. One is called the Richter scale, and one is called the Modified Mercalli Intensity Scale, often called the MMI. So let's do the Richter scale first, because this is the one you hear the most about on the news. So the Richter scale was developed in 1935 by a man named Charles Richter, and he worked in California, and he used math to compare the size of earthquakes. And so it's a logarithmic math scale that he uses, so it works on a power of 10. He assigned a number that would allow you to compare earthquakes. There's huge differences though between the levels. So if you look, we use just numbers 1 to 10. If it's less than 1, all the way up to 2.9, you really don't feel those earthquakes. They happen all the time. More than 100,000 of them a year happen. There's a lot of them that we never even notice, but they get picked up by the machines. A 3 to a 3.9 is felt by people, but there's not a lot of damage. Those are also very frequent, up to 100,000 a year. A 4 to a 4.9 is felt by all people. Anyone near the earthquake would feel it. There is some minor breakage, maybe things fall off the walls, or maybe a crack in a wall. Glass might break, something like that. So that's from 2,000 to 12,000 a year. 5 to 5.9, some damage to weak structures, maybe a deck or a patio or something like that. You see 200 to 2,000 of those a year. 6 to 6.99, anything 6 and above, you're really going to start to see some damage. So in a highly populated area with lots of people and buildings, you're going to have moderate damage. You might see people who are killed in an earthquake 6 or higher. So in the 6 range, 20 to 200 a year. Now, when you get into 7 to 7.9, you have serious damage over major areas. It's a large destruction zone. Loss of life is very common, and there are 3 to 20 of those a year. 8.0 and higher are severe earthquakes. They have massive destruction, major loss of life over large spans of area. These are the ones that you do not want to be in. And there are fewer than 3 of those a year, thank goodness, but when they happen, they're pretty traumatic. And the difference between like a 3 and a 3.2 is actually really big. So I wanted to show you this graphic. I thought that I found this online that I thought would be helpful to explain the differences. The Richter scale, I said, is a base 10 scale. So when you use the size in the graph, an earthquake that registers a 5 on the Richter scale has a shaking amplitude 10 times that of an earthquake that's a 4, and thus corresponds to a release of 31.6 times the energy. So sometimes you'll see people say that the numbers are off in the 30s, or they kind of give you different numbers. It is a 10 times the amount, but the energy changes. Okay, so if you are looking at these 2s, where this chart actually said there's about 1 million of them worldwide. That's only about 123 pounds of energy, explosive energy. If you look at a tornado, that's up here by like a 4 or 5. The Hiroshima atomic bomb released a little over 123 million pounds. And we have had earthquakes that have released more than that. So if you look in 1994, there was a big earthquake in California, Northridge. In 1995, Kobe, Japan. Loma Prieta, California, 1989. That was a huge one. I remember growing up. I was in middle school when that happened, and they made TV movies about it. It was a really, really, really big earthquake in United States history. Here's Mount St. Helens, okay? That much energy compared to Hiroshima. And you can look at these. The San Francisco Great Earthquake of 1906, it completely destroyed San Francisco, burnt it to the ground. They had started the whole thing over again. How about 1964 Alaska? If you're interested in earthquakes, I recommend looking up that earthquake. It was devastating. And then Chile had an almost 10 on the Richter scale in 1968. Catastrophic. Okay. So I thought this was a good graphic to kind of break down for you the amount of power that is released in these earthquakes. All right. I also mentioned the modified Mercalli intensity scale, and it was developed in 1931 by American seismologists Harry Wood and Frank Newman. This scale composed of increasing levels of intensity that range from imperceptible shaking to catastrophic destruction, and it is designated by Roman numerals. It does not have a mathematical basis, and instead it is an arbitrary ranking based on observed facts. So it is opinion and how people perceive the earthquake. The MMI scale assigns a value to a specific site after an earthquake has occurred to measure the severity to non-science people. Okay, so it tells you how much you actually experience. So let's say there's a 6.0 on the Richter scale earthquake at Westmoreland Mall. Let's say that is a 6.0 earthquake no matter what. The people who live right next to the mall are going to have a lot more damage than, say, people who live in Ligonier. Okay, so on the modified Mercalli intensity scale, there would be a higher Roman numeral assigned to the people who live near the mall because they experienced more damage. And people who lived in Ligonier would have a lower number because they experienced less damage. Okay, so it just depends on how the people feel the earthquake. And here's a scale that kind of goes along with that. Like a 1 to a 4 are not really felt. When you get into 6, 7, that is whenever people are having major damages. So you can look up the modified Mercalli scale if you wanted a little bit more information on that. What I would like for you to do in your notebooks is to create a T-chart, Richter scale on the left, modified Mercalli on the right. The big differences are Richter scale is quantitative, it's measurable, it uses numbers. Modified Mercalli is more qualitative, and it's looking at more of an opinion. The Richter scale measures rock motion, whereas Mercalli measures how the earthquake feels by people. We say the Richter scale measures the magnitude or how strong the earthquake is. Modified Mercalli measures intensity or the amount of damage done. And then the Richter scale uses numerals, so on a scale of 1 to 10, whereas the modified Mercalli uses Roman numerals. Okay, so make sure you get some information in your notes, and then we will finish up earthquakes tomorrow. Okay, thanks for your attention, guys, and I will see you tomorrow.